Okay, what an amazing introduction. Thank you, Yanei. Well, I'm going to share my screen first. Let me see if you can see it. Are you here?
Yeah, it's just loading, I think. We've got a blank. Okay, so now, yeah, we can see your slides, some results.
No.
Animal tracking data. Yeah.
Yes.
That looks great.
My internet connection is unstable.
It looks perfect.
Okay. Interrupt me if you can't follow me or something. So, well, I'm Sofia Ruiz-Suarez. I live in Bariloche, in Argentina. And today I'm going to talk about animal tracking data. So, well, I introduce myself. I'm a PhD student at the Institute for Research on Biodiversity and Environment here in CONICET, Argentina. I study Bayesian statistics with applications in animal behavior and movement. My advisor is Juan Manuel Morales here in Argentina, and my co-advisor is Vianney. So a little bit of what I'm going to talk to you today. First, I would like to introduce you on the background on tracking data and the study of animal movement, which are our motivations, why we decide to study animal movement and how we do that. Then I'm going to talk about the different kinds of data and the devices that are available to study animal movement. Then I'm going to talk a little bit about the SHIP project. That is a project that we conducted here in Bariloche with my advisor and other researchers. And finally, I would like to give you a brief introduction of some of the analysis and models that we use to analyze the tracking data. So the first question is why we study animal movement, why we decide that animal movement is interesting. So from an ecological point of view, animal movement plays important roles in the fitness and evolution of species, in structuring of populations and communities, and in responses to environmental change. So from a practical point of view, we are interested in the movement of animals for scientific reasons and for making decisions regarding the management and conservation of natural resources. So the next question is how we study animal movement. Well, and the answer is with technology. We use technology that is based in animal-borne telemetry devices. This technology gives us information about the locations and some external characteristics of the animals. And sometimes these devices also give us information about the internal characteristics of the animal, for example, the heart rate. The good thing of using this technology is that it helps us overcome many practical and logistical and financial challenges of direct field observation. I mean, it's not necessary to go to the field to observe every step and every move of each individual. But this data is a challenging data. Sometimes it could be tricky to attach the devices to some animals. For example, if you work with huge animals or aerial or marine animals. And then the data is always in high resolution and is usually with some error. So we need to live with those points in some way. So now I'm going to talk about the different kinds and devices that are available to study how animals move. I'm just going to talk about the devices that we use here in Bariloche, but I want you to know that there is much more technology if you want. So GPS data, I think, is the best known data. These devices give us information about the animal's location every certain time. They determine the longitude and latitude of every time. So they give us these spatial coordinates. This information, the GPS data, allow us to describe different trajectories of the animals. And it's really common that this information came with some error, something that maybe it's necessary to be aware when we analyze the data. And then here in Bariloche, we also use these devices that are called daily diaries. The daily diaries are devices that measure, well, several things. They measure acceleration, magnetic field, and they also measure some external characteristics of the animals. In our case, we have information about the altitude and the temperature of the environment. So, as I told you, the acceleration is the change in the velocity. In these devices is measured in 3 different directions: in surge, heave, and sway directions. So these allow us to classify the acceleration into different behaviors. Then I'm going to talk about how we do that. So the acceleration is measured as the static acceleration and the dynamic acceleration. So we can distinguish which acceleration is from the animal and which acceleration is from the earth. And this data is taken in a high resolution. So they present high temporal dependence, something that, again, we need to be aware when we analyze the data. Are you following? Are you hearing me? Are you following me? Because I have something that's saying me that I have an unstable connection.
Yeah, no, it's perfect for us.
It's good. Yep.
Okay. So, well, here in Bariloche, we use the daily diaries and the GPS. Okay. Now I'm going to talk a little bit about the SHIP project. This is a big project that my advisor and I, my advisor leads, and I am part of this project. And part of this is part of my PhD project. So the general aim of this project is to understand how livestock production depends on the movement of the individuals, their behavior, the climate, and the landscape. So to do that, we study a flock of 60 sheep from the northern Patagonia, here in Bariloche, Argentina. So the tools and the available devices that we had to study that were, well, 60 sheep. And we tracked the 60 sheep with GPS and daily diary devices. The GPS were programmed to record data every 5 minutes. And the daily diaries give us 40 data per second. And we had solar panels that we attached to those devices to charge the batteries. So how was the fieldwork? The fieldwork was divided into 2 different parts. The first part was we need to collect the track data, and then the other part was about to collect the direct observation data. So to attach the devices to the sheep, we use collars. And we attach the collars to every sheep. This wasn't easy because as how the accelerometers work, we need that the devices were fixed in the same position. Because if the device moves, the reference systems also changes. So we had to try different collars designs until we find one that allow us to fix the devices. It wasn't easy. So then, as these devices possess no mechanisms for data transmission, we then need to take the collars off to recover the data. Okay, then the other part, that was the collection of the observation data. We first measure some morphometric characteristics of every sheep, like length or height. And then every month we went to the field and we also measure weight and condition. The condition is an index of amount of fat of every sheep. And this index was measured by vets. And what they did was to touch like the back of the sheep, and they in some way they feel like the amount of fat sheep, and they give us a number between 1 and 5, and that was our index. And well, then finally, as we wanted to classify behavior from the acceleration data, we record videos to observe those behaviors. So then we need to watch those videos to determine the behaviors and the moments of the changes. So we attach the collars to every sheep. Then we measure the morphometric characteristics. Then we went to the field every month to measure weight and condition. Then we record the videos. Then we classify we record the videos. Then we went to the field to take the collars off. And then we classify the videos in a manual way to use this information to train our models. So now I want to show you one of our videos. I hope you can watch it well. So we marked every ship with a number between 1 and 60. That was the ship number 59. To then know which ship corresponds to which device. So something like that is a day in the field here in Bariloche, something like that. So now let's see some of the data. So when the experiment finished, we have monitored 57 sheep because 3 died during the experiment. And we have information for approximately 8 months. And as I told you before, we have data every 5 minutes. And what is plotted here, we have 5 different trajectories from 5 different sheep. Each color corresponds to a different ship. And those are the trajectories for a whole day. And we can see that they move in similar way. Okay, then we have the information from the daily diary devices. We record acceleration, magnetic field, altitude and temperature. And we have 40 data per second for 57 sheep during 8 months. And what is plotted here is one of the manual classifications from one of the videos. And what is plotted here is are different features derived from the acceleration data. Here, the first one is the mean bedva. The mean bedva is a feature that is a proxy of energy use. The second plot is the mean pitch, that the mean pitch is a proxy of the angle of the head of the ship. And the last one is the standard deviation of the mean pitch. And with different colors, we have like different behaviors. For example, the violet one is when the ship is inactive, it means that the ship is or sleeping, or maybe she's standing. So when the ship is inactive, the mean bedva is low. It means that the energy use is low. And the mean pitch is constant. That's because the head of the ship is quiet. And then we can see that the ship starts walking, and then the bedva increase and the mean pitch decrease. And then the ship starts eating, and then she again walk, and then she again eat. In this example, we don't have the fast walk behavior, but this is just one example. So something like that is our data. So now I'm going to talk a little bit about how to analyze this data. I'm just going to show you some models to classify the acceleration data in different behaviors. I'm not going to talk about the GPS data. And what I'm going to show you now is part of my PhD project. So as I told you before, the aim with the acceleration data is to classify into different behaviors. Why we want to know what the ship is doing, why it's interesting. Well, if we know how the ship moves and how the ship behaves and how it is connected with the internal conditions of the animals and the external conditions of the animal, like the environmental conditions, we can understand how to design strategies of livestock management in a better way. From a statistical point of view, the aim is to distinguish patterns in the data that belong to different behavioral states of the animals. So we want to recognize the moments of behavioral state changes, and we want to recognize the corresponding categories. So we have a time series, and we want to identify which are the moments in which our system changes from one state to another. And then we want to identify which are those states. So to do that, we use a supervised approach. So we use the labeled data that we obtain from the videos that we record to train the models. Okay. As I told you before, data possess high sequential correlation. So to take that into account in the analysis, we propose to classify the data using hidden Markov models. A hidden Markov model, or an HMM, is basically a model that has two different processes: a latent process, that is what we do not observe, and an observation process. And those two processes are connected by the structure of the model. In a hidden Markov model, the latent process is taken to be a first order Markov chain. So that's why we said we can consider the sequential correlation present in the data. For our system, the latent process is the behavior, is the state of the sheep. What is she doing, if she is walking or sleeping or eating? And the observation process is the acceleration data, or some features derived from the acceleration data. Well, a basic HMM can be modified in order to consider more dependencies of the data. So we also extend the HMM to an HSMM, and then we compare the classifications of both models. Why we thought that an HSMM could be a better option to classify our data? Because in our system we have like some behaviors have similar acceleration. For example, when the sheep is sleeping and when the sheep is standing, the mean bedva and the head pitch are similar. The mean bedva is low because the sheep is inactive, and the mean pitch is constant because the sheep is quiet. So the main difference between those two behaviors is the time that the sheep spends doing one or the other. Maybe the sheep could be sleeping for half an hour, but standing just for 2 seconds. So we thought that maybe a hidden semi-Markov model could improve the classifications. The hidden semi-Markov model, the difference between the hidden Markov model is that with the HSMM, we can explicitly model the duration that behaviors are exhibited via any valid discrete distribution. So if we assume that all our distributions are geometric, we obtain an HMM. That's why an hidden semi-Markov model is an extension of the HMM. So we first conducted a simulation analysis. The aim was to characterize in which scenarios the state predictions of both models, the HMM and the HSMM, differ, to understand when violating the model's assumptions can affect the accuracy of the classifications, when it was necessary to extend the HMM to an HSMM. So to do that, we simulated different scenarios of univariate time series from a two-state HSMM, which differ in the observation distributions and in the Sohn time distributions. For the observation distributions, we assumed that both were normal, and we changed the overlap degree between both. And for the Sohn time distributions, we assumed that they were negative binomial, and we did two different things. First, we modified the dispersion parameter in order to get distributions near or far from a geometric. In a negative binomial, if the dispersion parameter equals 1, the negative binomial is a geometric. So we changed that parameter in order to get distributions that were near the assumptions of the HMM or far the assumptions of the HMM. And then we also modified the mean and the difference between the mean parameters of the negative binomials. So some results that we obtained with regards to the overlap between the observation distribution, as expected, the performance of the models are lower when the overlap between the observations is larger. About the values of the dispersion parameters, we obtained that when one of the distributions is geometric, the differences between the models are lower, which makes sense because in that case, we are under the assumptions of the HMM. And finally, about the mean between M1 and M2. M1 and M2 are the means of the negative binomial distributions. We obtained that when the mean is high, the differences between the two models are not too important. However, as this mean decreases, the differences between the models increase. Okay, that was the simulation analysis. Now, I'm going to show you something of the models that we use to analyze our real data. So to classify behavior from the acceleration features, we proposed 4 different models, 2 HMMs and 2 HSMMs. For all of them, the latent process was sorry, for all of them, we consider 4 different states for the latent process, 4 different behaviors. The walk behavior, the fast walk behavior, the foraging is when the sheep is eating or looking for food. And finally, the inactive behavior. That is when the sheep is sleeping or the sheep is standing. We had to join these 2 last behaviors into one because we couldn't get enough observations of the sleeping behavior. So we have 4 different states. Then for the observation process, we consider autoregressive and non-autoregressive process for the HMM and the HSMM. And we consider 3 different features derived from the accelerometer data that were related to the head pitch and the mean beta. So we have 4 different models: an HMM with an observation process that is an autoregressive process for the 3 features. Then an HMM with non-autoregressive process for the 3 features. Then the HSMM with autoregressive process for the 3 features. And finally, the HSMM with non-autoregressive process for the 3 features. In all cases, we consider that the features were independent. And finally, to predict the behaviors, we use 2 different algorithms. The first one is based on global decoding, and it predicts the probability of the state and the observation. And the second one is based on local decoding, and it predicts the probability of the state given the observation. So here we have some of the results. These are the feature distributions for the different behaviors. The first plot, this one, is the mean beta that, remember, was the proxy of energy use. We obtain the lowest values for the inactive behavior and the highest for the fast walk, which makes sense. And we obtain the similar distributions for the walk and the foraging behaviors. Then here we have the distributions for the mean pitch, that was the angle of the head, a proxy of the angle of the head. The lowest values are for the foraging state. It's because the head of the sheep is down, the sheep is eating. And then for the fast walk and the inactive behavior, they seem to be quite similar. And then we have the distribution for the walk behavior that is like in the middle of the others. And finally, the standard deviation of the head pitch. We obtain the highest values for the fast walk, for the fast walk behavior. Then for the walk and the foraging behaviors, and the lowest values are for the inactive behavior. It makes sense because when the sheep is inactive, the head is quiet, and when the sheep is running, the head is moving. And well, finally, these are the results for the classification errors. We measure 2 different indexes to measure the classifications. We measure the accuracy to have a general idea of the performance of the classifications for the 2 algorithms. And we also measure a cross entropy index to measure the uncertainty over the classifications. So we didn't find the differences between the 4 models. They all classify quite well. We have high values of accuracy and low values of cross entropy. Maybe the HSMM with autoregressive structure has a little bit more of the cross entropy index, but they are quite similar. So maybe in this case, it's not necessary to extend the HMM to an HSMM to obtain better classifications. But I think that if we could get more observations for the sleeping behavior, I think that the HSMM should improve the classifications over the HMM. So that's all. Thanks a lot. And I don't know if you have any question or something you want to know.
No, I'd just like to say thank you very much. That was amazing, Sofia. I couldn't believe how I feel as though I understand what you do, even though it was like so complicated, and I definitely don't. But you just explained it all so clearly. So thank you very much. It was just wonderful. If anyone has any questions, feel free to put them in the chat. I might just get us started while folks are sort of thinking of their questions. But Sofia, I mean, you must deal with teams, right? You must deal with sort of biologists or sheep farmers and experts, as well as the stats side of things. How do you sort of navigate both of those worlds? What's the challenges in that?
Well, it's a good question. Really, I'm just the only mathematician here in Bariloche, and the rest of the researchers and the PhD students are all biologists. So I had to learn to interact with them. So I think that I feel like more